Hello and welcome back to Calculus. First, you already know I'd like to thank all the nice people that support this channel by liking and subscribing. It really helps a lot so that I can make more videos for you in the future. Today is the final video on derivatives. We will still use it a lot in the future. However, all the theoretical and conceptual things have already been covered. Just for this last video now, we will take a look at a real-life application of derivatives, specifically kinematics. First, let's answer the question, what is kinematics? Kinematics is the study of how objects move. A particle moving in a straight line is the simplest type of motion. To describe simple linear motion, you need three things: a starting point, a direction, and a distance. Now, let's dive a little bit deeper into the specific terminology, starting with the word path. Path is the set of points along which an object travels. After that, we have distance. Now, distance is defined by a particle. It's the length of the path between the particle and its starting point. Finally, we have the word displacement, probably the most misunderstood word in mathematics and physics. Displacement of a particle is the difference between the particle's position and its starting point. So, for example, if you run a complete lap around an athletics track, the distance you traveled will be the standard 400 meters. However, after you have completed that lap, your displacement would be 0 meters because your initial and end positions are the same. Displacement is actually a vector quantity, as it tells you the shortest distance of the object from its starting point. Distance, however, is a scalar quantity, as it only tells you the length of the path the object has traveled. Now, you may ask, what does all of this have to do with derivatives and mathematics? All of this seems like physics concepts. I can tell you immediately that displacement is related to another term in physics and mathematics called velocity. Now, if you have done physics before, you probably know that velocity is defined as the speed in combination with the direction of motion of an object. To put it more simply, your velocity would be the change in displacement divided by the change in time. Here, I use the lowercase s to define displacement and the lowercase t for time. Now, of course, whenever you see change in something over change in another thing, you automatically are going to be related to derivatives. Especially because derivatives are dy dx, or change in y divided by change in x. So immediately, if you have a velocity function v of t, you already know that this is going to be equal to the derivative of your displacement function. And now finally, we have one last thing called acceleration. To put it simply, acceleration is the rate at which velocity changes with respect to time, in terms of both speed and direction. And note, acceleration can actually be negative. and that just means you are moving backwards. So mathematically speaking, if you have the velocity function, once again v of t, you do its derivative and you're going to get the acceleration function a of t. So in our course, the most important thing in kinematics are these two things: velocity with relation to the displacement, and how acceleration is related to velocity. From this, we actually arrive at this double equation, where the second derivative of displacement is equal to acceleration, and of course the first derivative of velocity is also equal to acceleration. So that means the first derivative of displacement is your velocity function. All right, so now that we have the theoretical and conceptual stuff, we can take a look at a quick example. The example here says a particle moves in a horizontal line so that its position from a fixed point after t seconds, of course where t is greater than or equal to 0, is going to be s meters, where s can be expressed in terms of t as 5t squared minus t to the power of 4. And for number 1, we're tasked to find the velocity and acceleration after 1 second. So here we are given the displacement function, meaning to find the velocity we have to do the first derivative, and to find the acceleration we have to do the second derivative. And if it says after 1 second, it means I just have to plug t equals to 1 into velocity and acceleration functions respectively. So firstly, the velocity function first derivative of displacement is going to be 10t minus 4t to the power of 3. And when you plug in 1 into the velocity function, what you're going to get is 10 minus 4, which is 6. And I can tell you that the unit is going to be meters per second. Next up, to find the acceleration function, we have to do the derivative of the velocity, or the second derivative of displacement. In our case, we would get 10 minus 12t squared. And then, to determine the acceleration after 1 second, you plug in t equals to 1 into the acceleration function, and we get negative 2. The unit here is going to be meters per second squared. Now, for the next question, they asked us, determine whether the particle is speeding up or slowing down at t equals to 1. Now, since we have a positive velocity, however a negative acceleration, it means we are still moving forward. However, we're trying to accelerate backwards. This tells us that the particle is actually slowing down because of the opposite signs of acceleration and velocity. Next, they ask us to find values of t when the particle is at rest. What does that mean? If the particle is at rest, that means that the velocity is going to be equal to 0. So in our case, we would simply take the velocity function and equate it to 0. Here, I can tell you that there are two answers. One of them is going to be t equals to 0. It makes sense. In the beginning, the particle is going to be always at rest. And then the other answer is going to be the square root of 5 over 2. And this is approximately after 1.85 seconds. Lastly, they ask us to find the time intervals on which the particle is either speeding up or slowing down. So step number 1 here would be to take our acceleration function and equate it to 0, because this tells us the exact moment when the car stopped accelerating in front and started accelerating towards the back. Solving this, I can tell you that t is going to be equal to the square root of 5 over 6. And once again, this is approximately 0.91 seconds. Here we have constructed a table. We need to determine the signs of velocity and the sign of acceleration in different time intervals. Because as I have mentioned before, if you have two same signs for velocity and acceleration, for example, plus and plus, or minus and minus, this means that your particle is speeding up, whether it's in the positive direction or in the negative direction. However, if the signs of velocity and acceleration are opposite, so plus minus or minus plus, this means that they are counteracting each other and the particle is slowing down. So here we have three different time intervals, and the signs for velocity is going to be plus, plus, and minus. And on the bottom, for acceleration, we have plus, minus, and minus. So this tells you that when the particle was speeding up from 0 to 0.91 seconds, and after 1.85 seconds has passed. In the middle, between 0.91 and 1.85 seconds, this particle was being slowed down. So there you go. That's how you apply derivatives into a real-life problem. I hope this video was helpful. And from the next video, we are going to start with integral calculus. So I really hope to see you there. I hope you are excited and have a nice day. Bye.